Hey everyone, welcome to this explainer. If you're studying computer science, you've probably heard the term compiler design and maybe felt a sudden wave of anxiety. It definitely has a reputation for being dense, highly theoretical, and, well, frankly, pretty overwhelming. But today, we're going to take a deep breath and break it down simply. We're looking at the very front end of this process, an area called syntax analysis. Think of this not as some rigid mathematical hurdle, but as a really fascinating process of translating our human chaos into digital order. So relax, grab a notebook if you want, and let's explore exactly how we communicate with the machines we build. I want you to pause for a second and try to shift your perspective. When you and I write code, we see logic, right? We see flow and intention. But when a machine first looks at your code, it doesn't see a program. It literally just sees a massive flat string of text, just a chaotic sequence of spaces, letters, and symbols. So how does it get from that flat line of text to a deep structural understanding of your intent? How does it actually know that a certain block of text is a loop and another is an assignment? Well, that bridge from text to understanding, that's what we call syntax analysis. Section 1, the grammar of programming. Okay, let's dive into this. To make sense of that flat string of text, we have to start by defining some ground rules. And the absolutely crucial point here is understanding the difference between syntax and semantics. Semantics is what your program actually does when it runs. It's logic, its output, its ultimate meaning. But right now, we are entirely ignoring that. We only care about syntax. Syntax is purely about the proper form. It's the structural rules. Think of it kind of like English grammar. If I say, the purple cloud ate a loud car, that's actually syntactically correct. It has a subject, a verb, and an object, even though, semantically, it makes absolutely no sense. For this stage of the compiler, we just want to ensure the code is in the proper form. So, to define that proper form, computer scientists use something called context-free grammars. These are often written in a notation called Backus-Naur form, or BNF. You can really just think of a context-free grammar as a gentle, precise rulebook. It's a set of instructions that describes the hierarchical structure of a programming language. Instead of trying to understand the whole program all at once, it breaks the language down into smaller, nested, recursive parts. It brings order to what otherwise just looks like endless text. Let's look at a familiar friend. If you've written in Java, C, or JavaScript, you know this structure. If, expression, statement, else statement. A context-free grammar naturally looks at this and breaks it apart. It basically says, an if statement is just the concatenation of the keyword if, an open parentheses, an expression, a closing parentheses, a statement, the keyword else, and another statement. It defines the large, complex blocks of our programs by simply nesting smaller, super easy to understand building blocks. Section 2, building the syntax tree. Now, having a rulebook is great, but the compiler actually has to map out your specific code using those rules. Its first instinct is to create an exact, literal translation of your input. This is known as a parse tree. Notice how dense it is. Every single piece of the input is represented as a leaf on this tree. If your code had a parentheses or a bracket or a semicolon, it shows up here. It's highly accurate, but notice how incredibly cluttered it gets. It contains a lot of structural scaffolding that we just don't need once we actually understand the shape of a code. Now, what's really interesting here is the calming transition from that messy, literal parse tree on the left to the abstract syntax tree, or AST, on the right. The parser takes the literal tree and just strips away all the noise. Once the tree structure itself represents the relationships, like, knowing that an operation applies to the two numbers below it, we no longer need the parentheses or the brackets holding it all together. They simply disappear. The abstract syntax tree is just an elegant abstraction. It condenses the information, efficiently keeping only the pure essence of what is needed for the compiler to translate your code into machine instructions. By shedding those unnecessary tokens, the AST significantly lowers the cognitive load and the computational overhead for the machine. It becomes the clean, organized blueprint of your program. Section 3, dealing with ambiguity. Of course, building a beautiful tree isn't always completely straightforward. Consider these classic math problems. 3 plus 4 times 5. Does the parser build a tree that adds 3 and 4 first, or multiplies 4 and 5 first? Or look at 34 minus 3 minus 42. Does it associate to the left or to the right? If the parser doesn't have strict rules, it might actually build two completely different valid trees for the exact same line of code, which would result in wildly different answers. A parser simply cannot function with ambiguity. It requires absolute certainty. To protect the machine from this confusion, we design our grammar rules with built-in tiebreakers. We establish precedence, telling the parser that, hey, multiplication always groups before addition, ensuring it sits deeper in the syntax tree. We also establish associativity, meaning operations like subtraction are strictly read left to right. By tweaking how the grammar rules recursively call each other, we force the parser into a single, definitive, and peaceful interpretation of the math. No guessing required.
And this brilliantly illustrates exactly how we do it in practice. Notice how the grammar presented here isn't just a flat list of operations anymore. The rules for multiplication are literally nested under a different name, like term and factor, than the rules for addition. We have rewritten the grammar to mathematically group the operations. We haven't changed the language itself at all, but we've removed the ambiguity completely. The structure of the rules now perfectly dictates the structure of the tree.
Section 4, Organizing the Chaos. So we have our rules, and we have our trees. But what happens when the human breaks the rules? I absolutely love this quote from the source text. The parser must respond gracefully to finding that its input cannot be generated by its grammar. It's incredibly reassuring, isn't it? The compiler isn't some angry judge punishing you for missing a semicolon. It's actually a system built with the full expectation that you will make mistakes. Its job isn't just to succeed on perfect code. Its job is to fail gracefully on imperfect code. This is achieved through error recovery. When the parser hits a wall and realizes a sequence of tokens violates the grammar, it doesn't just crash and give up. A well-designed parser will attempt to infer what you meant. It might insert a missing token or delete a rogue character, not to rewrite your program, but just to stabilize its internal tree so it can keep parsing the rest of your file. This way, it acts as a helpful guide, returning a complete list of syntax errors in a single pass, rather than making you fix them one agonizing compile at a time. Section 5, The Beautiful Bridge. As we bring all these ideas together, take a step back and really look at what a parser is doing. Syntax analysis is far more than just rigid academic theory. It is the beautiful, graceful bridge between human thought and digital execution. It takes our messy, flat, ambitious strings of text, applies a calm set of rules, and builds an elegant, structured tree that the machine can actually understand. It literally brings order to our creative chaos. So the next time you hit compile, don't just brace yourself for errors. Ask yourself, what kind of invisible, magnificent tree is the machine building out of your thoughts right now? Thanks for joining me for this explainer, and keep exploring.